All right, my name is Ilya. I am the co-founder and CEO of a company called Parse. And today I will talk to you about why we started Parse, what we built, how we built on an AWS, and what challenges we faced, and what challenges we plan to face in the future with our AWS deployment. So what is Parse? In short, Parse is a better way to build mobile applications. We provide a set of SDKs for all of the major mobile platforms, iOS, Android, Windows Phone, mobile web, what have you. And these SDKs allow developers to access a suite of cloud services in their own environment without leaving Xcode, without leaving Eclipse, whatever their favorite language is. They stay in that language and they get a suite of really powerful cloud services that let them do everything they would need to do to build a mobile app and have it access the world, the back end. Oops. This thing's a little laggy. All right. Where am I supposed to point this? So anyway, why did we build Parse? So we built Parse out of our own frustrations with mobile development. Mobile development is painful, it's repetitive, it's expensive. Companies all over the world are reinventing the wheel, building the same functionality over and over again. So for example, when was the last time you recommended an app to your friend based on the login screen? Hey man, this app is so great, you have to download it. It did such a good job at associating metadata with my Facebook credentials. And then get this, it sent me a push notification. It's just table stakes, right? Every app out there has it, every app out there needs it, and it's just the default for the world of mobile. That said, building that sort of functionality is actually quite difficult. It takes time, especially because there's so many different devices, so many different platforms, so many different gatekeepers, so many different flavors of even Android. So building the same stuff over and over again is painful, it's expensive, and doesn't drive value to the user, right? When you download an app or an app succeeds on the App Store, it doesn't succeed by the way of its back end. It succeeds based on the front end, whether it's a useful, fun game or a useful app. The front end matters, that's where you differentiate in the market. You don't differentiate based on push notifications, you don't differentiate based on storing data, you don't differentiate based on this nitty-gritty stuff. And in the mobile world, there's a particularly large skill gap in what it takes to build a great mobile app and what it takes to build other sorts of applications. So for example, take the example of an iOS game, right? So a great iOS game has a great UI, it has great mechanics. The person who developed it is probably an expert in Objective-C, great at UIKit, great at OpenGL maybe. But there's a lot of other nitty-gritty stuff that they have to build. So they have to build something like a system to cache writes on the client and replay them on the server for scenarios where you're on the subway and you're playing a game and suddenly data needs to get synced once you have connectivity and you get off the plane. All this stuff is painful, and the person who's good at Objective-C, who's good at the UI, who's good at OpenGL, is not the guy who's good at building this nitty-gritty stuff in the client, and he's certainly not the guy who's good at building this stuff on the server, and he's certainly not the guy who's good at putting all the pieces together. So companies that are successful in mobile tend to end up with very specialized teams. They have an iOS team, they have an Android team, they have a back-end team. All these folks have to coordinate, and a lot of the work that happens gets reinvented over and over again, right? So the system that might be caching writes for an offline scenario on iOS probably looks pretty similar to the system on Android, but it's a different language, a different team. There's a lot of work being done over and over again. So that's the thesis behind Parse. We want to make a platform where we abstract away all this stuff for you. We give you a layer that you build on top of so that you can focus on the UI, you can focus on the important stuff. We take care of all the nitty-gritty stuff. The sort of crux of what we've done is this product called Parse Data. Everything else is built on top of it. And the idea here is that we let you store data to the cloud, retrieve it, sync it between devices as simply as humanly possible. Let's take the example of an iOS game developer, right? They might have a single-player game. It has no networking capability. It's just a great game. It's fun to play. But you can't play with your friends. You can't share high scores. You can't do anything. Now suppose you want to add the very simplest sort of multiplayer experience, which is maybe sharing high scores with your friends. What do you have to do? You're an Objective-C developer. Well, you have to spin up a server. You have to spin up some kind of stack like Rails or Django or whatever it may be. You have to write this API in a language that you might not be familiar with, whether it's Ruby, Java, Python, whatever it may be. You need to figure out how to synchronize data back and forth between the client and the server. You need to figure out the offline stuff that I talked about. You need to wake up in the middle of the night if your app explodes in China. You have to do all this stuff that, for you, isn't really core to your competency, and this is just for the very simple use case of building a high scores list. What if you wanted to do more? So that's where Parse comes in. We try to make this much, much easier for mobile developers. So Parse data is the underpinning of all of our product. It lets you store data, sync it across devices in a very simple fashion. So here's an example. Unfortunately, the font got messed up, but you get the idea here. So these 4 lines of Objective-C create the score class and score object. They put some points in the points field. They put my name in the player name field. And then the save and background call saves it to the server. These 4 lines of JavaScript basically, Objective-C rather, take care of all of the stuff that I just mentioned. And if you guys, any of you are familiar with Objective-C, 4 lines of Objective-C doesn't get you anywhere, anytime. There's really not much in the world you can do with 4 lines of Objective-C. But what we've done is we've provided an SDK that lets you do so much stuff with just 4 lines. So, for example, this will cache this object locally. This will retry the network if it is unavailable for some time. This will do all the serialization back and forth. This will set up the schema on the back end if you've never, ever saved a score before. We do all sorts of stuff for you right out of the box. And when you want to query it back, we have a similar system. It's essentially an ORM in Objective-C, in Java, whatever it may be. So, getting all the scores for players named Ilya is also a few lines of code, and you get them back in your native Objective-C objects, or your native Java objects, your native JavaScript objects. You don't have to deal with a network. You don't have to deal with serialization at all. So, the other side of this equation that we've built is the data browser. So the data browser lets you inspect, modify, and update the data that is flowing into your app. And so this is super useful for many reasons. It's useful for developers, but it's particularly useful for the non-technical people in your organization. So suppose you're a content producer and you're updating assets in your news application. You might need to otherwise have a system that's tailored to you to ingest new metadata, new assets. With this data browser, all you do is interact with this. It's an Excel-like spreadsheet view of all of your data. You log in, you add data, you add rows, whatever it may be, you upload some photos. You don't need a special system. You don't need an engineer. Suppose you're a game producer. Your main calling in life is tweaking the cost of cows to get more money out of 8-year-olds. Tweaking that number, how much the cow costs in your app, you can do yourself. You don't need a special system. You don't need to talk to an engineer. Excuse me. If you're an intern and you're working for some social app and you need to scrub user-generated data to make sure that it's OK for public consumption, you could have a special system for this, or you could just log in and use this data browser. You can create, update, delete records. You can upload photos. You can upload files, whatever it may be. You get a full Excel-like view of all of your data. All right. So the other big thing that we do is push. So push is a huge pain in the ass in the mobile world. If any of you have dealt with Apple's push notification services, they're not easy. Essentially, the API is a binary SSL socket. You construct 256-byte packets to it, and you get very little in response. It's not very high level at all. On the Android side, it's the Wild West. Google has a solution for some subset of devices but it doesn't work with the Kindle ecosystem. It doesn't work with other ecosystems. It's a huge pain. So what we do is we give you one API, one interface for all the devices in your system to do all sorts of interesting high-level push notification functionality. So not only do we let you just push fast and easy, but we let you do things like scheduling, targeting, all sorts of functionality that's otherwise difficult to build, especially difficult to build at scale, and difficult to build in a way that's consumable by non-engineers. So here's an example of just 3 lines of Java code to send a push notification. It's that easy. This is also a place where we've done a lot of work to make the rest of the organization empowered to send push notifications, to interact with the app, to use it in ways that they would otherwise need to talk to an engineer or have some special interface built for them. So suppose you have some app, and its main purpose is to notify folks about upcoming shows, and you're a concert promoter, and you need to tell folks about an upcoming show. This is the interface that you would go to. You would compose, preview, schedule a notification, all inside this pretty interface. And we let you do lots of interesting stuff. So suppose you wanted to wish everyone Merry Christmas, right? That's not the same time across the world, right? There's lots of time zones in the world. We do that all for you. So suppose you wanted to send a push notification for Merry Christmas. You can say, send a push notification on the 25th at 11 a.m. local time. We'll take care of figuring out where the device is, when to send it, when to queue it up so it gets delivered on time for you. You don't have to think about any of that stuff. We also have really powerful targeting. So suppose this concert promoter, again, wants to get even more advanced. They want to send a push notification to everyone in Boston who's above drinking age, who likes these 2 bands, Yo La Tengo and Calexico. We can do this right out of the box in a graphical user interface. You can also do the same thing with an API. It's basically a query language that queries your devices based on whatever metadata you've put into it. You can query across it and send push notifications based on it. Parse social is also a big part of what we do. So like I said before, login screens are sort of de facto just like a standard in every mobile app. In general, identity and security are standard in every app in general. But all these things are painful to do, right? Having folks log in with their username and password, storing that securely, resetting the passwords, having folks log in with Facebook, having folks log in with Twitter, all that stuff is painful. Getting it all right is even more painful. So suppose you have a situation where you let folks log in with Facebook, they log in, they do some things, then they associate their Twitter account, and they share something on Twitter, and then they go to their iPad, and they want to log in through Twitter instead of their original Facebook. We'll do all that association for you and maintain that user identity, have all the metadata there associated with whatever authentication systems they've hooked up. And so this also extends to things like Active Directory, arbitrary OAuth. It's not just the typical social networks. So these are 4 lines of code, depending on how you format, to sign up a user in Objective-C. You give a username and password. Typically, it would come out of a text field. And then you call this function, sign up in background. Once it calls back, that means we've created the user record for you. We've associated the data on the device that hooks the device to the user. We've stored their password. We've done everything for you. And then whenever they create objects, you can create objects with an ACL where that object is only owned by this user, no matter what way they've authenticated originally. And we've also gone as far as to do some UI-level components where we give folks out-of-the-box components like this login view controller. You can customize it to take either username and password, Facebook, Twitter, or any combination of the above. You can skin it. You can make it beautiful. It's up to you. This is really just a way to get up and running as fast as possible. Nobody in the world wants to build this stuff. So we are the platform that builds this stuff for people. We do it once. We do it right. And you can use it and get going faster. So you might be wondering, OK, great. A lot of the stuff you've shown me is sort of client side. Obviously, you can't just do everything on the client side. So that's true. What we've done is we've built this thing called Cloud Code. And what we've done is we've made it really, really easy to put business logic onto our servers in our own runtime. So the way it looks is it's essentially our JavaScript SDK and your JavaScript snippets that you give to us running in our virtualized environment. So this is what a function looks like to, say, average the reviews of a movie in your database. So you construct a query, you create a condition that looks at only the reviews for a particular movie, you do a find. Once that calls back, you calculate the average, and you send it back up the wire. What you don't need to think about here is you don't need to think about the database. You don't need to think about the indexing. You don't need to think about the serialization. You don't need to think about the client-side caching. The client just calls one line of code to say, get me the average reviews for this movie. We do all of this for you. This is literally all you have to write. You don't have to spin up a Rails stack. You don't have to spin up anything. This is all you write and give it to us. Very powerful. So we've also built a bunch of integrations with other companies because we also don't want to reinvent the wheel ourselves. So there's a bunch of companies that have done a great job with particular services like sending an SMS, sending email, whatever it may be. And we wanted to make that integration as simple as possible. So this is what it looks like to send a SMS with Twilio. You instantiate your credentials, and then you write, depending on your formatting again, basically one line of code. You don't need to think about the integrations. You don't need to set up a server that talks to both Twilio and Parse. This is all it is. And so our goal here is to partner with companies that have done their respective parts correctly so that we don't reinvent the wheel and so that no developer ever writes boilerplate code while doing one of these applications. OK, so who's using it? Well, we have 40,000 apps on the platform. Right now, we're doing about a few billion API requests per month and hundreds of millions of push notifications per month. So we've reached some pretty serious scale. There's obviously a long way to go. But we've done all this in about 6 months of being out of beta. We've also gotten some really serious companies on board to entrust us with their mobile applications to build on top of Parse and buy into this new way of developing applications. So folks like Home Depot, Tom's Shoes, the Food Network, the Travel Channel, the Green Bay Packers, Armani. There's a whole slew of big brand apps. This morning, I heard that all the Sesame Street apps are going to be using Parse. So we're very excited. Your kids will be Parse-powered pretty soon. Whoops. Let's go back. This thing seems unpredictable. All right, so I will talk about how we did this. 1 second. So let's take this example, these 4 lines of code that do all this functionality, and let's trace it through our infrastructure so you get a sense of how Parse is built, what it is that we're actually doing for you, and how everything looks on the back end. So like I said, these 4 lines of code do all it takes to store some score on our system. So this is our high-level overview of our infrastructure. So the request comes in through the internet, obviously, from whatever device it may be. It might be an iOS device, an Android device. It might be the REST API. It might be a JavaScript website, whatever it is. Comes in, and it comes in the form of just an SSL HTTP request, usually JSON encoded, with our internal sort of language. Hits ELB first. ELB forwards it on to one of our web servers. Our web servers run Nginx. And in the case of API requests, they don't particularly do much. They forwarded it on to one of our app servers using HA proxy. Our app servers are where most of our IP lives. Not most, but a lot of it. They're running Ruby, and they do a lot of the heavy lifting. So they take one of these operations where it's a create, read, update, delete, and there's various flavors of each of those. or a user sign up, or a reset my password request, or a call this special function called average reviews, whatever it may be, it unpacks it and forwards it along to wherever necessary. In this case, it's a simple create request. And I'll talk about some interesting things that we do with just a simple create request. So if you noticed before, hopefully this thing doesn't jump too much, these are just the 4 lines of code you need. You don't need to set up a schema ahead of time. You don't need to tell us about any indexes ahead of time. You can literally go into Xcode, write these 4 lines of code, and we will store your data, and it will all work. There's no setup to be had. You don't have to log into the website and draw a bunch of diagrams or write a bunch of SQL statements. You don't have to do anything. So the way that works is we have a lot of logic in the app server to maintain this layer of consistency on various levels. So the first part is maintaining a schema. So the first time you send us this thing, we notice, hey, OK, you're sending us a new object. It's of type score that you made up. It has 2 fields. Points is an integer. Player name is a string. Great. We'll set that up for you. If you ever send us another object where player name is a Boolean or a dictionary or some wild thing, we'll error out for you, and we'll maintain the schema for you. On the other hand, if you wanted to add a field, you wanted to say, I'd like to store the location of every one of these scores. You don't have to tell us about that ahead of time. Just start sending it. We'll figure it out. We'll infer it for you. And that's a big part of what these app servers do, is they maintain the schema data that comes in through these requests. Another big thing about what we do is we make it so that developers never have to think about indexing. So if you noticed in the previous example, no mention of indexing. There's no interface to set up an index. There's nothing. So we watch your query traffic. So if you start doing queries based on these scores, and you start asking all the time, OK, show me all the scores whose name starts with Ilya and who lives in San Francisco, we'll watch that query traffic, and above some threshold, we'll realize, OK, this is clearly a pattern in the app. We need to create an index on those fields in this collection. So that's a big part of what we do, is automatic indexing. You never have to think about this. You shouldn't have to think about it. And we take care of all that for you. So in terms of actually storing the data, most of the, or all of the app data, so the data that's owned by our developers, owned by our customers, lives in a Mongo cluster. We use MySQL for various Parse level things, like folks' credentials, website-related things, but it's never really in the critical path. The critical path stuff is always memcached. Let's see. In terms of parse data, we also support a lot of helpers to get photos and videos and other just plain binary unstructured data into the system. That stuff flows through S3, or flows to S3 through our app servers, but it's fairly straightforward. So let's move on to push. So what do these 3 lines really do on the back end? So again, more or less, the request travels as expected to the app servers. Except this time, the operation isn't create, read, update, or delete. It's send a push notification to some subset of people. In this previous example, there's no actual conditions on it, so it'll send to everyone in the app. But you can put any arbitrary conditions on it. You can say, send this push notification to everyone named Ilya. You can say, send this push notification to everyone whose score is above some certain threshold. We have a very rich query language that's used for both the ORM and for sending push notifications. So anyway, the app server receives this request, and it enqueues a job into Redis. And the job looks something like, send a push notification to all devices that match this criteria. And then we have these things called channel servers. These channel servers are sort of misnamed, but what they do is they expand this query. So they talk to Mongo. They figure out what are all the devices that need to be talked to. And they, in turn, enqueue their own jobs back into Redis that are more of the form, send this exact packet to this exact device. So on the iOS side of things, the device is identified by their own Apple token. On the Android side of things, we manage everything. So we hold open sockets to all of the Android devices that are in our system. We don't use any of the Google Cloud messaging stuff. We do everything. So we actually have an open socket to every Android device that uses our platform. So the channel/expansion job will enqueue a job back into Redis that's like, send this exact packet to this device identified by this unique ID. And so in the iOS side of things, if you guys aren't aware, Apple is sort of the gatekeeper to push notifications. So we talk to their servers. We hold open sockets for every app, and we push as many push notifications as possible over to them. We sort of funnel it over to them. On the Android side of things, like I said, we're actually holding open sockets directly to the device, and we send those over as fast as possible as well. So there's a lot of parallelism here. We can get, I don't know, tens of millions of pushes out in a matter of seconds. So there's a lot of parallelism, lots of jobs running to eat these things off the queue and get push notifications out as fast as possible. Yeah, that is it. All right, so let's look at this cloud code example. So this is a piece of JavaScript that one of our developers might write. It's basically vanilla JavaScript, except that our Parse SDK is baked in as if it were part of the language. We have also some other utilities that are baked in as part of the language, things like Twilio and Mailgun, many more in the future. But it's essentially vanilla JavaScript. OK. So things travel to the app servers here as well. And then they get forwarded to another set of servers called the Cloud Code servers. These things are running essentially isolated V8 environments. So we've customized V8 to no end to load our own environment, to restrict various bad things that people could possibly do, to do a lot of accounting around resource usage, CPU time, real time. You can also do external HTTP requests, so you can talk to the outside world and integrate with whatever API you like, whether it's Salesforce or Active Directory or whatever, you name it, you can talk to the outside world in our runtime. So interesting part there is that we have essentially a bunch of V8 customized instances running this code. There's a lot of supervisors to make sure that you don't do anything crazy. The talking to the outside world is piped through Squid, so you also don't do anything crazy and use Parse to overload someone else's servers. We wouldn't want that. Yeah, so that's how that works. All right, so I will talk about a few AWS-specific challenges that we faced in building Parse. We faced lots of challenges in building Parse, but we're at an AWS conference, so I'll talk about some AWS-specific things here. So these are the four: resiliency to zone failures, EBS performance, visibility, and chefing everything. If you're not familiar, Chef is a tool to automate server deployment. The Python equivalent is Puppet. And we went through a long period of time using that. So let's talk about resiliency. So I'm sure most of you know, the idea here is to spread your system as much as possible across all of the availability zones in your region. We are currently only in the EC2 East region, but we are fully spread across all the zones. The idea here is pretty simple. Just at every part of the stack, we have some level of indirection that makes sure that the next part of the stack is spread across all zones, and that requests flow in a way that if one of those zones dies, we're all OK. So the first step of that is ELB. So ELB takes requests from the outside world and forwards it on to one of our web servers. The next step is moving from web to our app servers. So that's HA proxy. And then there's a bunch of other parts of the components of the system. So in the example of, say, the Cloud Code servers, we have our app servers doing custom stuff to monitor the health of all of the Cloud Code servers. We round robin them. We pull them out if they're unhealthy. In the case of, say, the Android servers, where we hold open sockets to hundreds of millions of devices, what we do there is we use Route 53 DNS to round robin so that if a particular zone dies, the end devices will eventually resolve to a new Android push server and get back into the system. In general, we've done a lot of work here. This is probably the hardest part of building on AWS, is making sure that you're resilient to failure. It's also the hardest part of building any distributed system, making sure you're resilient to failure. So one thing we're doing that's AWS specific, in general, we've mostly kept everything just on vanilla EC2. Obviously, we use ELB and S3. We've mostly kept everything vanilla EC2 for sort of our own purposes, to have as much control as possible, to be able to expand to other data centers if necessary. But one place where we plan to use the AWS solution is moving our MySQL stuff to RDS. In our case, MySQL is not necessarily in the critical path. The stuff that is in the critical path, the data that lives in MySQL that is in the critical path, tends to get cached, super read-heavy, never written. So we're planning to move that to RDS so that we don't have the headache of maintaining the failover ourselves. We would also love to be able to slave in and out of RDS, which I don't think is yet available. But in general, we hope to move that over pretty soon. All right, so the other big thing, EBS performance. So having a very write-heavy infrastructure, also using Mongo, makes us pretty susceptible to variance in I/O performance from EBS. And so we did all the typical stuff. We used ephemeral storage wherever possible, where we didn't need durability, where we didn't need to snapshot our actual data. For the actual important stuff, the Mongo data, we did the typical thing where we used RAID 10 across a bunch of different volumes to make sure that we sort of washed away the variance as much as possible. We also wrote a lot of custom logic to make sure that the Mongo instances always had the most active collections in memory at any given time. This includes our slave replicas. So when a failover happened, we are in a state where the most active collections on the master also end up being the most active collections on the slave whenever that switchover happens. So that said, even with all that work, we ended up with graphs like this. So on the left side, we've got latency in seconds from 0 to 2.5, basically always at 200 milliseconds. But once in a while, we would spike up to something like 2, which is pretty unacceptable. This would happen because EBS would slow down for a bit, Mongo lock contention would go up, and things would grind to a halt for 5-10 seconds. Not too bad. We've done a lot to make this easier, make this better, but still a little bit painful. The saving grace for us has been the recent announcement of provisioned IOPS. So if you take a look at this graph, you'll notice that the y-axis here is a different order of magnitude. It goes from 0 to 0.6 at the top. So not only have we gotten rid of this annoying spike, this variance in performance, but we've also dropped our average latency in half. So basically, provisioned IOPS are awesome. We enjoy them very much and are very happy to move more and more of our stuff onto provisioned IOPS. So visibility is another big thing. So as a startup, at some point, this was our network operations center, a piece of paper on a concrete wall that says everything's great. This was a long time ago. But over time, you have to develop monitoring. You have to develop visibility into your own system. And so we did the typical stuff. We set up Nagios. We set up Ganglia. We set up alerts for various parts of the system. Whenever memory on any machine went up, we would get paged. Whenever anything, anywhere got paged. The one thing we didn't have that AWS really helped us with is we didn't have a great sense of what was the overall, just big picture performance of our system. Right? To do that, you kind of need to step out of your own system and measure the end-to-end stuff, which is not easy, right? You might move to another data center, have some script that pings your real infrastructure, but you're never going to get sort of the real view because anything you do is going to be synthetic. The sort of end-to-end queries that you run through your own system are always going to be some synthetic, out-of-date thing that you've made up. So what's really helped us here is leveraging CloudWatch on ELB. So this is now our slightly less ghetto knock, in that it actually exists. But this has actually been super useful for us. So what this is doing is it's pulling stats from ELB using the CloudWatch API. The top graph is our requests per minute. Under that graph, you'll see some red stuff. I don't know if it comes out well in this iPhone photo. But those are the errors per minute, where errors are our fault and not a developer's fault. Our developers make lots of errors. We certainly try to minimize those, but these are our problems. And then on the bottom is just the end-to-end latency. So basically, as far as ELB is concerned, is how long is everything else taking? So it seems simplistic, right? These are pretty simple, high-level stats. But organizationally, this is super powerful. Having this in our office has made a world of difference. When any of these spike to some unexpected level, the entire monitor goes red. So it's basically visible to everyone in our small 20-person company. The sales guys know, our office manager knows. It's really made sure that we have a great handle on the overall high-level performance of our system. And it's really not easy to do unless you hook into something like ELB and use CloudWatch to pull these stats yourself. All right. The other big part of what we've done is automating everything. When we first started out, we were 4 guys, we had 1 machine, and everything was easy to maintain. Eventually, we've ballooned to hundreds of machines. And at some point, we had to move from 1 machine to images that backed a couple of machines to actually automating everything. So we used Chef to do that. And it's allowed us to do some pretty gnarly migrations. So we moved from Ubuntu 10 to Ubuntu 12 in 1 day across hundreds of machines. We did that because there was some nasty kernel panic that was really plaguing us. But having these cookbooks, this automation has really made life easier for us. So I'll talk about 3 parts where AWS-specific technology has helped us be even more awesome on this front. So the first one is we're moving to a system where instead of having our servers spin up, depending on the role, web, API, push, whatever it is, they spin up, they get all the packages they need, they get all the services they need, and then they have to pull down the code that we've recently deployed. We're moving from a system like that to a system where actually our internal continuous integration service, Jenkins, stamps out AMIs automatically so that when we want to spin up more servers, they have all the latest stuff. They have the latest code already there that's passed test, that's ready to go. This is super powerful for auto-scaling, which we'll talk about in a second, because just time to getting up a server is really crucial if you want to auto-scale well. So that's been great. So we also have this push-button process for increasing Mongo capacity. So we snapshot our master Mongo all the time, and then with one push of a proverbial button, we can get another server to spin up from that snapshot, stripe itself across many EBS provisioned IOPS instances, join the replica set, and get moving in a matter of minutes. This is super powerful. Managing this stuff yourself is a nightmare. Another part of where AWS has really helped us out is we use Route 53 pretty extensively, like I talked about before, but we also use it internally to get out of the mess of dealing with EC2 DNS. It's just annoying to use EC2 DNS. So we have Chef, whenever it brings up a new server, register with Route 53 to give it a sane internal DNS name. So this has been really helpful because you can refer to servers in emergency scenarios or in scaling scenarios without pasting, some 40-character EC2-IP-whatever string. It's more of a sensical name. All right, so future challenges. Auto-scaling is a huge part of what we do. So like I said, we don't make you think about databases, indexing, schema, or anything. We also don't make you think about scaling. So a lot of other platforms like ourselves and analogous ones kind of push it on to the user or the customer, right? There's some lever that you have to pull to get more instances of whatever they have or get more resources allocated to you. That's not really auto-scaling, right? You're not going to be awake when you need to be to pull that lever. So we have always from the start made sure that our developers never have to think about this sort of stuff. So one challenge of this that I talked about earlier is just getting your servers up and running as fast as possible. The other part is sort of the discovery side of getting your servers up into the system, right? Every little arbiter in the system, the HA proxy, the ELB, the round robin stuff that shoots to the cloud code servers needs to know that, hey, there's a new server ready to serve more traffic. And so we do that now, but it's kind of painful. There's a lot of configuration to manage. There's sort of a lag in getting it to reload. What we want to do here is use Zookeeper, where all of those indirection points subscribe to a Zookeeper instance and get notified whenever a new server comes up. When it comes up, it'll notify them automatically, and they'll add it to the pool. So there's some really interesting pain points here. On Saturday, we had an app of ours that was built by Home Depot, advertised during all of the college football halftimes. This is Thanksgiving Saturday on ESPN. So clearly not something that's easy to scale for, right? An app goes from nowhere to being on primetime live TV, every 3 hours in one random day. None of our team watches college football, so it's not like something we were prepared for. There's other scenarios. So that one is kind of the situation where if you put it on yourself, you just don't know when your customers are going to launch a big thing, promote a big thing, get featured by Apple, get featured wherever, have a primetime ESPN commercial. You just can't plan for that kind of stuff. So this is a big challenge for us. We're doing well, but we could always be doing better. The other scenario is that just the nature of mobile usage patterns makes auto-scaling and just traffic patterns unpredictable. So we have this app in China that has, I think, 10 million devices subscribed to push notifications. It's an app that lets you watch TV shows on the phone. And so for most of the week, there's really little traffic. But once a week, when the latest episode of whatever the popular Chinese show comes out, they send a push notification to 10 million people. So 10 million people open the app and do some level of query traffic to get the listings and get the link to watch the show. So that's painful. What's even more painful is that 5 minutes later, that's all over, right? So it's just literally from 0, 10 million, back to 0. So dealing with that is definitely a big challenge for us, but it's also a big part of just the value add. If you have an app that's serious, you run into this sort of stuff yourself, and it's very hard to do. It's very hard to do in a way that you don't have a full staff managing it for you. So this plays into managing cost control versus slack capacity. So we do our best to auto-scale, but obviously we have to run with some slack capacity to absorb just the initial spike before our machines can get up and running, right? It's not instantaneous. It's quick, but it's not instantaneous. So balancing cost control versus that as the platform grows is an interesting challenge. I think we'll be using a lot of the billing APIs in the future to really understand how our costs scale as we grow our overall traffic and also decrease the time it takes to auto-scale. And then going multi-region is big for us. We have a lot of customers in Asia, particularly Japan, China, Australia is coming up, so we're actually really happy about the Sydney data center. So for us, going multi-region is a really big priority. We need to get to places that aren't in Virginia to lower latency and get more presence in other places. And the challenges here are pretty typical, right? More operations, more importantly, having state consistent across data centers that are not necessarily tied by the highest bandwidth of links. So yeah, those are our future challenges. I think that's all I have for you guys. Before I take questions, I will say that we are hiring. We are a small team of 20 folks in San Francisco. We are having a blast doing this. We are growing incredibly fast. All of these challenges are real. All of those customers are real. Sesame Street is coming on board tonight. Like, a lot of these things are happening just day in, day out. So if you are bored at your job, please come talk to me. Parse is a very exciting place to work. We have some folks here that work with us. They would love to talk to you. We're hiring across the board. Also, my colleague Charity is going to be talking more about our Mongo-specific stuff. I think tomorrow at 5, the code thing is DAT203. So she'll be able to talk more extensively about Mongo specifically and how we're scaling it there. With that, I will take questions. Yes?